So, today I will demonstrate polarimetry experiment. See, aim of this experiment is basically determine the specific rotation of an optically active substance and find the concentration of an unknown solution of the same substance. Okay. So, that means this specific rotation of optically active substance that we have to find out, and we can also find out the unknown concentration of the solution of that active optically active substance. Okay. So, theory for this experiment is very simple. So, basically if we know the definition of specific rotation, then it is a working formula easily we can derive. So, definition of the specific rotation is the basically specific rotation of the optically active substance solution is defined as the rotation theta of the plane polarized monochromatic light of wavelength lambda produced by a column of solution of length 1 decimeter, means 10 centimeter, and containing 1 gram of the substance per cube centimeter per cc of the solution under experimental conditions, means at the temperature of the solution and for the wavelength used for this experiment. Okay. So, if this is the definition, so then S equal to, so basically angle of rotation of the plane polarized light when it is passing through the length of the solution column, if that is L centimeter, so per decimeter means L divided by 10, that is the decimeter. So, theta divided by this L divided by 10, and then per unit concentration, okay, means 1 gram of the substance per cm cube, that is the nothing but the concentration. So, divide by concentration C. Okay. So, S equal to 10 theta by L C is not least count L C. L is the length of the water column in centimeter and C is the concentration of the solution. Okay. And concentration of the solution is basically m by V. M is the mass of the solute. Okay. Here we will take sugar and then divide by volume. Say if you take some volume, so generally we can take 100 cm cube cc. So, then for 20% concentration, so m has to be 20 gram. Okay. So, for different concentration of the solution, if we can measure the rotation of the plane polarization light, so that means concentration versus the rotation, that angle theta. So, we can plot a graph that for different concentration what are the rotations. Okay. So, theta by C, that we can get, that is nothing but the slope of this graph. Okay. So, you will get straight line and slope of this graph is theta by C. Okay. So, theta by C, that slope of the graph will be L S by 10, L S by 10, that is the slope. So, that slope we can find out from this graph. Now, that S will be slope into 10 divided by L. Okay. L length of the solution column in centimeters. We have to remember that is in centimeters. So, we can calculate the S. Okay. And for you can do the experiment for unknown concentration of the same solute. Okay. In our case, it will be sugar. So, that unknown concentration of that solution you can find out. Okay. So, we will put this solution in the tube tube for containing the solution. So, its length is known to us. Okay. Now, all conditions are same. So, for that solution we will measure the angle theta. Okay. So, experimentally we will measure the angle theta, and if we put this theta in graph. Okay. So, for that theta, from this graph itself what will be the C concentration you can find out from the graph itself, or you can, if from this graph slope is calculated. Okay. So, using this not slope, yeah, slope is calculated, and then from there you are finding out the specific rotation. So, using this experimental result of specific rotation, you can find out the concentration of unknown solution. Okay. So, this is the theoretical part of this experiment. Now, we will use polarimeter. So, this polarimeter is basically, it was used by Lorentz, Lorentz, okay, not Lorentz, Lorentz. Okay. So, in polarimeter what things are there? Okay. In polarimeter basically you have collimator. You have collimator, that means slit source and then lens. Okay. So, it is producing parallel rays. Okay. Then we have a polarizer. So, that is nothing but the nickel prism. That is nothing but the nickel prism. So, what is nickel prism I described earlier. Okay. So, basically it produced the polarized light, plane polarized light. Okay. So, now when this light, it is unpolarized light, when, so we will take sodium light. So, it is a nearly monochromatic light. When it will pass to this nickel prism, it is a polarizer. So, light will get plane polarized light. Okay. So, that means electric component will be in a particular direction. Now, it will pass through it is called Lorentz half shade. Okay. Lorentz half shade. So, it will pass through this Lorentz half shade. What is Lorentz half shade? I will explain. So, then this light, this polarized light, basically it will pass through the tube containing solution. Okay. So, it will pass through this solution. Okay. So, then whatever the angle of the plane polarized light was, okay. So, here due to passing through the solution of the optically active solute, so this electric component it will rotate. Okay. So, that means plane polarization, that it will rotate by angle say theta. Okay. So, now it will rotate by angle theta, then it will, another nickel prism we will use as an analyzer. Okay. So, it will pass through this analyzer. So, if initially this polarizer and nickel prism, another nickel prism analyzer, if they put parallel, their optics axis are parallel, then what will happen? So, if there is no rotation here, so we could get light, intense light. Okay. We could get intense light. Now, if we rotate this analyzer, by 90 degree. So, then it would be cross position. Then we should not see any light. Okay. We should not see any light. Okay. So, uh, so but if any rotation is there, then in cross position basically you will not see the dark. There will be some brightness. To make it dark, you have to rotate more. So, how much you have to rotate to get it completely dark or completely bright? Okay. So, that will be basically the rotation of the plane polarized light. Okay. So, that we will measure. Okay. So, now question is, then using only this polarizer and analyzer we could do the experiment. So, why we need this Lorentz half shade? So, Lorentz half shade is basically, it makes more sensitive this detection. Without this also one can do this experiment, but it's to get this complete dark or complete brightness is since we are seeing through the solution, okay, it's become hazy, it's difficult to identify, this dark position, complete dark position and complete bright position. So, it is difficult. So, if we use this type of Lorentz half shade, so this changing of the its sensitivity of detection of this distinction of this color or not color is the intensity. Okay, it's a much more easier, and that's why we tell is much more sensitive. It's make this system is more sensitive, and that was discovered by Lorentz. So that's why it's we tell this Lorentz polarimeter. Okay, and this called Lorentz half shade. Now, what is Lorentz half shade? Okay, Lorentz half shade basically it's a half of this circle. So, half of the circle or semicircle is basically made of quartz, and its optics axis, quartz and calcite, these are uniaxial crystal, and it has optics axis. So, optics axis are parallel to the surface. It cut in such a way. So, these optics axis are parallel to the surface. Okay, and other semicircle is basically made of simple glass. Okay, it does not, this light, its polarization does not affect by this glass. Okay, in general. So now, if you use this half shade, here this quartz thickness, one is the condition is that this optics axis will be parallel to the surface. Another, thickness of this plate is such that it's basically half wave plate. Half wave plate I described. Half wave plate is basically when O ray and E ray will pass through it will introduce lambda by 2 path difference or phase difference pi between E ray and O ray. Okay. So, that is the half wave plate. So, another plate, quarter wave plates, lambda by 4 path difference introduced. Another full wave plate means lambda path difference is introduced. Okay. So, from this polarizer, when polarized light, plane polarized light, so its electric component say this. Okay. So, it will fall on this half shade, Lorentz half shade, okay, this way. So, here this way. So, when it is falling here, so it is falling on the glass plate as well as falling on the quartz. So, it will pass through this plate. So, when it will pass through this plate, so this electric component through the glass, it will not change anything. So, it will be equal intensity when it will go other side. Okay. But this part, the part which is falling on the quartz side. Okay. So, if electric component direction is this one, electric component is this direction, and optics axis is this direction, right. So, now when this light, plane polarized light falls on the quartz, okay, so it divided into two rays, O rays and E rays. Okay. O rays and E rays, you know, this one is sigma polarized light, another is pi polarized light. So, this basically this component, this will be divided into two component, perpendicular, mutually perpendicular two component. So, E component along this direction. So, it is the basically normal to the optics axis. So, it will be E ray, O ray, and another component is this. So, it will be basically parallel to the optics axis. So, it will be E ray. Okay. So, this ray, plane polarized light ray, when it will fall on the quartz part. Okay. So, it will break into two parts, E ray and O ray. So, it is the entering, during entering, this is the situation. When it will exit through the thickness of the plate, so other side exiting part. So, what will happen? There will be phase difference between E ray and O ray by pi. That means, if I keep this one with respect to this, if this one changes phase pi, so this direction will be in opposite direction. So, this dotted line. Okay. So, this will change the direction after going out, when it will come out from the this plate. Okay. So, now one component E ray is this component, when it is coming out, another component will be this. Okay. So, resultant one you will get this one. Now, you see, but for glass part there will not be change, it will be in this direction. So, you will get in glass part, so when it will come out, so electric component will be in this direction, and this quartz part, the electric component will be in this direction. And this is basically this direction is normal to the this direction. Okay, original direction. Okay. So, these two basically are normal. So, if it make angle theta, so other one also making angle theta with the optics axis, right. So, now this is the situation when it is coming out, from the Lorentz half shade. Okay. Now, here say this tube containing solution. So, initially you do not take solution, just take simple water. Okay. No optically active solute. So, what will happen? So, when it will pass through it, there will not be any rotation. There will not be any rotation of the electric component or plane of polarization. Okay. Plane polarized light. So, there will not be any rotation. So, then it will come to the analyzer. Now, this is the analyzer part. What we will do? So, when it is coming out, falling on the polarizer, okay. So, say polarizer, this this is the polarizer, this is the analyzer. So, same thing, nickel prism. So, if it is optics axis, say initially this direction. Okay. If it is this direction, so what will happen? For this direction, optics axis, that means a component of this electric component along this direction, that will pass through. So, component will be, so from glass part, that component will be E cos theta, and for the other half quartz part, so it is this direction. So, this direction, that also component will be E cos theta. So, from both halves, so when we will see through the telescope, we will see this basically image of this half shade, image of this half shade. So from both half equal amplitude is coming out. So, that means it will be looks equally bright, it looks equally bright. Okay. So, if this is the starting point, now if I rotate this analyzer, its optics axis will rotate. So, now I am at this situation. So, this situation is basically of equal intensity, this situation is basically of equal intensity, right. So, why equal intensity? Because these components are, this angle are same. Now, when I am rotating, so for this position, okay, now you see component from this half and component from other half, they are not equal. So, you will see the variation of the intensity of these two halves. So, when I will come this position, so then what will happen? So, optics axis will be parallel to the electric this vector in the quartz part. Okay. So, that means this part will completely exit, will go, come out. Okay. And this other part is perpendicular to the optics axis. So, you will not get this component pass through this analyzer. So, that means this half, glass half will looks dark and this quartz part will looks bright. Okay. So, from equal intensity, now next stage I got this one half is bright, one half is dark. Then if I continue the rotation, I will get this position, optics axis. In this position also you will see this equal angle of this electric component in both half. Okay. So, from both half this E cos theta, so in this case I think it will be E sin theta. So, E cos theta I have written. So, it should be E sin theta, and in this position it will be E cos theta. Okay. So, that means main thing is that both are equal, component are equal. Okay, from both half. So, again at this position I will get the uniformly bright of this both half. Now, again I am continuing the change. So, this it will change, intensity will not be uniform. So, it will change when I am in this direction. It is basically 90 degree with this, where we got this both half equally, this both half, one half was dark and one half bright. So, now it will be just one half will be dark, one half will be bright. So, it is the opposite direction. Okay. Because now glass part, that electric component will pass through, because optics axis is along this, and this component is perpendicular to the optics axis. So, this component will not pass through. Okay. So, this quartz half will be dark and this half will be bright. Okay. Now, so that means uniform and then dark bright, then uniform, then dark bright. If I continue, so it is basically initial position to it is now I am at 180 degree. Okay. So, again I will get uniform, because at this position, okay, I will get uniform situation. Okay. So, then if you continue, then again I will get this situation. Okay. 180 degree opposite to the dark bright situation, I will get again dark bright situation. Again I am continuing, then I will get uniform. Okay. Again I am continuing, I will get this position dark bright situation. So, I will come back to this again 360 degree. So, this means 0 position. So, in one complete rotation, I am getting 4 times uniform, 4 times uniform. One is this, and then second is this, then third is this, then fourth is this, okay, from uniform situation, okay, in both half. So, and dark bright dark, so this also will get 4 times, 2, 3, 4, okay. So, I will demonstrate what I explained, okay, what this half shade is doing, okay. So, in our case, so what we will do, we will actually see the uniform for detecting the rotation, measuring the angle. We will actually see the uniform situation, both half are uniformly bright, okay. So, if we take that standard, so what we will do, always we will do this 360 degree rotation, then we will take 4 reading, okay. Wherever we will get this uniform situation, we will get this 4, okay. For water, that we will do, we will note down the reading, okay. Now we will put the solution. First we will put this solution of highest concentration, okay, and then we will do this, okay. So, because now this will be rotated, this will be rotated, okay. So, that rotation actually, so that will change basically, this electric component will rotate, okay. So, now our uniform situation, to get it, so we have to also rotate the polarizer, analyzer by this angle to get the uniform brightness on both half, okay. So, that way we will find out the concentration versus the angle of rotation, okay. For different concentration, at least 4-5 concentration we will do. Then basically that is the experiment we have to do, and for that procedures, so we have to one procedure we have to follow to prepare the solution. Initially, as I told, highest solution of highest concentration will prepare, say 20% or 15%, say 20%, okay. So, now we will dilute this solution to get the lower concentration, okay. So, that is the calculation I have shown here, okay. If C1 is the initial solution, concentration of the solution. Now, I want to make C2 that concentration. C1 is greater than C2, means C2 is less than C1. Then, if I take X, if I take this volume of the solution of concentration C1, if that is X, okay. So, then how much water, distilled water I have to put in that solution to make the concentration C2. So, that amount of water, which amount of water I have to add. So, that is basically here details I have written. So, that will come C1 minus C2 divided by C2 into X, okay. So, using this formula, we can prepare solution of different concentration. So, from C1 to C2, then C2 to C3, where C3 is less than C2. So, that way we can go for lower and lower concentration of the solution, and for each solution we will do the experiment, and then finally you can just pour water arbitrarily and make the solution, or you can pour some more sugar to make the unknown solution, okay, and do the again measurement. So, you will find out the theta for that unknown solution, and knowing the theta, you can find out the concentration from the graph or calculate from the using the experimental value of specific rotation. Okay. So, here are this experimental data recording. So, length of the polarimeter tube that is given, or you can measure using the scale. Okay. So, whatever, so that you should write. Wavelength, whatever you are used, so we will use sodium light 5893 angstrom wavelength. Room temperature you should note down, okay, of the yes. So, we expect that solution temperature, room temperature will be same if we do not cool or heat it. So, then vernier constant of the polarimeter. So, there will be circular scale and there will be vernier. Okay. So, vernier constant of the polarimeter you have to find out and write. Okay. So, then table rotation of the plane of polarization when tube contains distilled water. As I told, distilled water, okay, reading for fast illumination. In some polarimeter there are 2 vernier, in some polarimeter 1 vernier. So, as I told, there will be 4 uniform illumination. So, but you can take reading for 4, you can take reading for 2. Here I have written for 2. Okay. So, 2 you remember. So, whenever first one you are taking this second illumination, we are that meaning is at 180 degree. Okay. After 180 degree rotation, whatever the reading you are getting, that is the second one. Okay. So, generally this first, this actually 4 uniform illumination you will get. So, 2 of them are basically weak intensity and 2 of them will be bright intensity, okay, highest intensity. But in our case it is difficult to distinguish that intensity. So, anyway, so we will take 2, so 180 degree apart from each other. Okay. So, you note down this reading, take the observation 1, 2, 3, okay, for first illumination, uniform illumination, and for second uniform illumination you take the reading. Okay. So, this mean reading for this distilled water R0 and this R0 dash. Okay. So, then you do the experiment for different concentration. Okay. For different concentration, now for first illumination, second illumination, take 2, 3 reading, okay, and then find out the mean value of this, mean value of the of R. R is the basically for first illumination and second illumination. So, R and R0, there R0 and R0 dash we have considered. Here also you can consider this R and R dash. Okay. So, now rotation theta will be R minus R0, theta will be R minus R0, and for other case R dash minus R0 dash. Okay. So, they are 180 degree apart from each other. So, whatever angle you will get, that should be same. Okay. It will, so average of these two will be the mean theta for one concentration. Then start with the second concentration, repeat the experiment. So, find out the mean theta for at least 5 concentration, and then sixth one you should know, you should do this experiment for unknown concentration, okay, and find out the theta. So, that is the experiment you have to do. So, now for determining the specific rotation from the plot as well as the unknown concentration. So, you just make table concentration versus the theta, you plot graph, from graph you find out the slope. Okay. Now, this slope you use for calculating the specific rotation, and using this specific rotation you can calculate the concentration of unknown solution, where experimentally you have measured theta for this unknown solution. So, you can find out the concentration of unknown solution. Okay. Then you have to calculate the error. So, this is the S equal to tan theta by LC. Okay. So, basically del S by S equal to 2 del theta by theta plus 2 del L by L plus 2 del M by M plus del V by V. Okay. So, that is the formula for error calculation. How it has come I have shown clearly, because C equal to M by V. So, you are measuring mass and the volume. So, you have to, so always error you have to convert in the parameter which you are measuring. Okay. So, and 2 is coming because we are taking the difference of 2 readings. So, that is why 2 is coming. So, using this formula you can find out the error. Okay. So, now I will show you the experimental setup and demonstrate the experiment. So, this is the experimental setup of polarimeter. So, whatever I told, so I think again I have set the camera. Okay. So, here, so this is the polarimeter. Okay. So, in polarimeter what things are there I explained. You have collimator, you have telescope, in between you have polarizer and then half shade. So, that is inside you cannot see. Okay. And then I have put the basically you see this is the tube containing solution. So, it's a water is there. So, but here the same thing we have put with a solution of sugar of 20% intensity. Okay. So, now then we have analyzer, and after analyzer we have telescope. So, through telescope whatever here from mobile camera, whatever this you are seeing, so that basically you are seeing the image of the, you are seeing this half shade plate. Okay. Half shade plate. Okay. Now, here there is a scale, circular scale, and there is a vernier. So, here is the, I can see this, how many are there, I think 10 or 10 divisions are there, and here the circular scale is the 1, yes, it's a total 360 degree, 10 it's a 1 degree, 1 degree, and it's the 1 degree, and this one is telling that 0 to 60, it is 0 to 60, but I can see how many divisions in between. Okay, this is telling is a one division. I think this 10 divisions is there, 10 divisions is there. So, one has to find out the vernier constant from this. Okay. Vernier constant is so 1 degree by 10. Okay, because vernier total division is 10. So, it is a 0.1 degree. So, it will be 0.1 degree. Okay. So, this polarizer, not polarizer, that is analyzer basically, that is attached with this scale. Okay, with this vernier. Okay, if I am rotating this vernier, you see I am rotating this vernier. So, that means this I am rotating the analyzer, now what here the spot you are seeing in camera. So, that is the half shade one, it is half shade plate you are seeing. Okay. I am trying to make slightly bigger. Yes, it's slightly bigger. Okay. So, Now, whatever for this half plate I told you, so I will try to demonstrate. Okay. So, I am starting from here, this reading it is a 0, you know. So, now I am rotating. I am rotating in say this direction. Okay. So, you start to count and see now. Okay, let me see what I am going to get. Okay, first at this position I am getting, you see, half is bright and half is dark. Okay, so this is one. So it's a must be parallel. This optics axis must be parallel to one of either one of the electric component. Okay, so two electric component will come, one from the glass and one from the this quartz, and they are mutually 90 degree. This angle is 90 degree between these two. So I got this one. Okay, and this I am getting around 27 degree. Okay, now I will continue. And then you see I will get a position where both half are uniform. Now this I can tell this uniform position. Okay. So this angle is around, I am seeing the 60. Okay. Now I am continuing, you see, I am getting another position where you are getting this half is this, now next half is dark and other half is bright. Okay. So this is the second position I am getting where is the electric component, one electric component is parallel to the optics axis, other one is perpendicular. Okay. So I will continue, then I should get one uniform position. So this I can take, yes, this I can take uniform position. Okay, yes, uniform position I can take. Okay, then I will continue. I will continue. And then I should get the half is bright and half is dark. Yes, I lost it. No, I think this is the position. This half is dark and this half is bright. Okay. So this third time I got. Okay. Now third time I should get the uniform one. Yes, this is the uniform one. Okay. This third time I got. Okay. Then so yeah, I got disturbed, but I will try to, yes. Okay. So uniform one, then I am continuing, then yes, I think I missed that one, or contrast is not good. Yes, here the contrast is not good, it seems. I think I have to, yes, I think here one position I am getting, yes, contrast is, yeah, now probably it will be better. Yes. So I think I have to just, no, I lost the contrast basically. Okay, so I think we have to set it. This now I am in original position, it seems 0. Okay, this other half I got dark and bright. Anyway, so I think just quickly I will rotate. So this is I think quickly if I just rotate and see the variation of this uniform, then no, I think this something is happening. So I will show you that I was showing that 4 uniformly bright both half and 4 half is bright, half is dark. So that condition should arise. So if I start from here, so it's 330 degree. So it's a uniform region. So if I continue the rotation, so I am getting this position where you can see this half is dark and this half is bright. Then again, yeah, it's I think more, it's becoming more prominent. Let me check it whether I am getting another uniform. Yes, here I am getting another uniform. So if I continue, I am getting the dark this other side and this side bright. So then I am continuing, then I am getting the uniform, it's uniform, okay. So then I am getting the another position where one half is, I think this the find out, this half is dark and other half is bright. So if I continue another uniform position I got. So no, this I think this is the uniform, better uniform. So if I continue, so I will get one another position where this half is dark and this half is bright. Okay. So this way there will be 4 times of uniform region and this 4 times of half is dark and half is bright condition. Okay. So that is the important for concept for the half shade plate, okay, Laurent half shade. So now I will remove this camera, okay, and I will just explain the experiment. So first what we have to do, actually we will measure the, you see, length of this tube, okay, using the scale. So I think this is not the difficult part. I think this I have to measure between these two ends. So it's the, I think if I put 0, so it is in this case I am getting reading 18, but water is up to this. Yeah. So I think one has to, before putting water, one has to open it and see the, I think here I can see, yes, okay, another solution is there. So this generally it's a 20 centimeters, either you can measure or here it is given this one, it's generally 20 centimeter this length, or you measure and find out this. It's a difficult to measure this way. I don't think this is the length. It's the length should be something. Yes, it's yes. So length from here to, I think water is from starting from here to here, okay, at this two ends. So that is 20. I can see this is 20. Okay. So this you have to measure or it is supplied, and then so here basically the similar tube. So here this 20% concentration of solution we have put here, and using that one I was showing you this 4 region. So first you have to, the same tube, okay, first you have to take this water. For water you have to find out this uniform shaded region. I cannot see. So, I think this is the position to put. Yes. Yes, now I can see, but no, no. No, I have to put it properly. So, I am not able to. Oh, okay. So, I think this is the flat edge we have to put down. So, then only you can, it will be in center, column will be at center. Yes, I can see. So, from here there will not be any rotation of that one. So, all the time, so here only one electric, no rotation, but I think this same way you will get this 4 uniform and but at some angle. So, I will set at a, yes. So, I will find out the first illumination, say uniform 1. I think this is the position I will note down, and another reading I will take this just 180 degree opposite. Yeah, this is the another position I am getting. I am getting, yes, uniform illumination. So, I have to take this reading. So, this is R0 reading, okay. So, for illumination 1, uniform illumination 1 and uniform illumination 2. Now, this is done as per this one, because noting down the reading is not difficult one, So, this table one, just as I showed, this put water and then do it, okay. And then I have to, so if you use the same tube, so remove this water and solution you have to prepare. Generally we take this, you see, there is a scale here of cm cube cc. So, it is a 100 cc, okay, and now 20 gram sugar you can put in 100 cc, or 10 gram sugar you can put 50 cc, okay. So, make 20% solution, okay. So, this is the solution as I told. Yes, I think, which one is solution? I confused, but hopefully this one I have taken in my hand. So, you put this solution, okay, closed it, and now try to find an uniform, but it looks the uniform in the same place. So, I think it may not be the sugar one. I think this could be the sugar one. Anyway, yes, it's changed probably. Yes. Anyway, so if you bring this, go to this first illumination and see this, find out the first illumination, okay. I think this would be the first illumination, then note down, go at 180 degree approximately, and there for second illumination you take the reading. So, this reading you take few times, okay. At this position you can take few times, or rotate and take 2-3 times and take average of that one, okay. Now, you take out this solution, prepare the, if you have more solutions, here I have more solutions, okay. So, I will put the distilled water. I have to calculate what percentage I want. So, I will, so from after calculation I will make it, okay. I add water into the solution. First I have to, I think this is the solution, and you, if it is 20% solution, so you take this solution of say some 100 ml or 50 ml, okay, of that solution, and calculate that to make it 15%, what is the water I have to add. So, you put water into that. Okay. So, make it solution, uniform solution. Okay. And then you change, you change this previous solution and put this solution and repeat the experiment. You repeat the experiment for 5 solution of known concentration, and then you do the sixth one, same way. So, taking reading is very easy if you identify the uniform region, and only here in this experiment main part I discuss and demonstrate that what is the function of a Laurent half shade, and how we can explain that uniform illumination, or half is uniformly illuminated and half is dark. Okay, we are getting 4 times uniform one and 4 times this dark bright, bright dark, this just exchanging the one. So, how we are getting that one? So, that I explained theoretically, and I have demonstrated that one. So, that is the main part to understand that one, and other rest of the things is easy. Also preparing solution, also one has to from higher concentration of solutions, how to get the lower concentration of solutions, that also I describe. I think this is the simple experiment, but it is a very nice experiment to find out the specific rotation as well as the concentration of unknown solution. Okay. So, I think I will stop here. Thank you.